Hello everybody and welcome to the first talk here in Hall 3. Our speaker is Swally, and in his talk he will address the history, the programming details and the hardware internals of one of the first game consoles on the market, the Atari 2600. Give him a huge round of applause. Here's Swally.
Hello. Hello. So this is what I want to talk about today, the Atari 2600 video computer system. Yes, it's really called that way. So I'm going to talk to you about the history, the hardware, and how you can write programs. Some first steps on how to get there. So why do I want this talk? Well, the idea came from two different aspects. One was Michael Stahl, who inspired me to do a talk about retro computing when he did his talk about the C64. And the other one is, why did I choose really the Atari? Because it is very well documented, the CPU, and the video chip is as well, and the video chip differs from anything else that you've got in any other hardware or any other gaming console. And this is the main cause. So, first of all, I got to thank you to all these guys. They did the pioneering. I just took on of their work and did the talk. And there are a lot of sites concerned about the varying aspects of hardware, video gaming in general, and specifically even on programming on the 2600. So let's start with the history. Short about Atari history. Atari was founded by Nolan Bushnell and Ted Dabney in 1972. The first, it was founded because they wanted to produce what is now known as Pong. The first, this is recognized as the first worldwide popular video game. And though it's not the first at all. The same goes for the Atari. It is also thought of as the first gaming console for home, but this isn't. There was the Fairchild Channel F was further, but this was the one that really got the huge success. Between 1972 and 2001, Atari had an arcade game division, which was the basic, or one of the main fields of industry where they worked in. And some of the games were also implemented for the Atari 2600. So let's start with the design history. Well, their first release was a home version of the Pong game, which was a success and a failure both. It was a success because it was the first game that really got into, first video game that got into people's homes. But it was more a failure for Atari because it was cloned very fast and they couldn't get much money out of it. So in 1975, they decided to produce a home game console based on a programmable design using a CPU. They codenamed it Stella after the bicycle of one of the engineers. And when they started designing, three processor designs were considered. The Intel 8080, the Motorola 6800, and the MOS 6502, which was an independent company once the design started, but between that and the release of the Atari, the whole MOS company got bought by Commodore so they could produce the PET computer and later the C64, VIC-20, something like that. And one of the key issues, what they wanted was it should be really cheap so that a lot of people not into video gaming would also consider buying one. So the basic design was set up in 2 days with the core team of the engineers together with Chuck Peddle of MOS. He was the man who designed the 6502. And both the CPU and the chipset were off-the-shelf components. If you take a look at nowadays consoles like Wii, Xbox, or the PS3, all are custom designs. So this is, back then it was off-the-shelf components. So, but the main thing, MOS got the deals because they were significantly cheaper than the others. The first offer was about $15. Atari sank the price to $12, whereas the competition got them to, or wanted to have $150 to $200. The guys at Motorola were sure that they want to get the deal because they were a bit cheaper than Intel, and they didn't know about MOS. So a week after they learned that they didn't get the deal, they sued MOS for patent infringements. But what still needed was the chip responsible for video and audio. There were no off-the-shelf components available at this time, so J. Miner designed one. J. Miner is also known, or better known, as the father of the Amiga. And he did it using breadboard technology. We have a picture of that later. And it was a rather expensive design phase because it was very tedious work to do. And it took quite a lot of time. But when the finished design was transferred into a chip, this resulting chip was easy to produce. And it was named TIA, short for Television Interface Adapter. So this is what a breadboard looks like. And this is just a binary counter. So imagine if you want to put a whole video chip on this one, that you really got to need a huge size of it. This is what the finished die looks like. And Atari is a part of pop culture. Though they were not the first on the market, this was the Fairchild Channel F, but they were the first that achieved really broad distribution. And it was released in 1977. And after the first release, the PCB design and also the casing was constantly redesigned, but the last version is still 100% compatible to the first version. And I knew back in the 80s, Atari was a synonym for home gaming. I knew back in the playground, when I was a kid, there wasn't, do you have a home game console? No, it was, do you have an Atari? And it was discontinued at the end at 1991. So it was in production for more than 14 years. And this is the longest, this is a console that's remained the longest in production. There are about 500 games that were programmed. If you're going to count in bootlegs, NTSC PAL conversions, stuff like that, you can get estimated to over 10,000 different modules. About 7,000 have been counted by one website. So this is what the first Atari looked like. There you see the module, you're going to plug it in there. And this is called the 6-switch model because there are still some difficulty switches on the front. In the next revision, they did not get moved away because it is still 100% compatible, but they have been moved to the back, which is better to see by the next revision, which is just another different color. So you're going to see there and there the difficulty switches. This was the last one of the original Ataris that was produced. If you want to go and code on real Atari hardware, I suppose that this is the console that you're going to use because it is technically the most advanced and it's really easy to modify for an AV output. The others still need some more. But this is for about parts 2 to 3 euro. You can build your own AV output. This is the Atari Flashback. So when Retro really got on the way, Atari also wanted to make some money of it, and they put a whole series of Flashback consoles. This is the Flashback 2 Plus, which differs from the original 2 just by a different game selection. The Flashback 1 was not really an original Atari 2600. It was a NES system on a chip design where the games has been ported to. The Flashback 2 is an ASIC design of the original hardware. And the Flashback 3, which is gone on the market this year, is an ARM-based computer which just runs an emulator. So, back in the days, there was this green meadow where they're going to put on new games. So where did they get their inspirations from? Well, first of all was to port some analog games, call them, something like chess or checkers, and also there was an attempt to port the video pinball. So this is what these games looked like. Sports were a very nice thing where they got their ideas from, and most of the sports have been implemented more than once. So there's boxing and real sports boxing, real sports soccer and Pelé soccer, and so it's nice to compare them. So we have that on the next slide, and probably the biggest selling title there was Decathlon, the Real Joystick Killer. So here we have basketball and soccer in the different year. So this was really from the early days. The double dunk is more sophisticated, but the most interesting part is compared to soccer. On the soccer, on the Pelé soccer, you have 4 players, three field players and a goalie, and the field players are always stay in this formation, so you move all of them at once. 6 years later, they got more sophisticated. The other players were controlled by the computer. You just controlled 1 player, and there were 6 field players and 1 goalie. So another huge origin of games was to franchise other titles like movies or cartoons like Spider-Man, and even something like the Muppets. And the first Star Wars video game was for the Atari 2600. And but there's no roundhouse kick. I tried it, I couldn't get it. So this is what the games look like. This is the first Star Wars title. So you're going to play your fighter against the AT-AT, Spider-Man, Smurf, and this one is Rails of the Lost Ark. Though it doesn't really look like much, it's one of the best adventures program for the Atari, and it's still a fun title to play today. But the biggest section was to port arcade games, but it was not really porting, but it was just a re-implementation of the original game idea. So let's just compare two games. I can say one of these conversions sucks, in my opinion, and the other one has really gotten very well. As I put on the slides, I say from the view of the games, you really couldn't tell which is which. But Donkey Kong, in my opinion, sucked because the original has 4 levels, and the Atari clone only has 2, the first and the last. And Popeye includes all 3 levels, and they are also very fun to play. But this is the part you really want to get an Atari for today. These are the original titles. They are really invented for the Atari. The most important part there is you have the most original titles were just another space shooter or something like that, but there were really some really nice pearls in there. Haunted House is a nice adventure survival horror game, is it also called. Pitfall is a classic, and Adventure is the one I'm going to introduce you in depth to. So this is what these games look like. About Yard's Revenge, there's a nice thing to know. There's this energy barrier you have there, which blocks your shot. The developer wanted to have some random data, but space in the cartridge was really short, so what he used as random data is what you see there is program code used as a table. So let's take a look at adventure. Why did I choose adventure as an example? Because it's the ancestor of all action adventures. So when you play Zelda, the original one was for the Atari. It is still a fine game to play. Okay, it will not take you as long as Zelda to come through. A skilled player can do the easy version in less than a minute, and the more complex. But this is just an introduction. The real level can be the real game setting can be done in about 5 minutes, something like that. But till you get to that point where you can do it in 5 minutes, you have still some things to learn. So it will get for the first time you get it through and think you're done. It is about an hour. The original author of this game had put on a small website about this game, where he also includes slides for a lecture he gave about this game and the Atari development in general. So, how do you play it? This is you. So, you start as an adventurer in front of a castle, and your job is to bring the enchanted chalice back to that castle. For this, you have a world consisting of 29 screens, like the first one you saw. There are 3 castles, 3 mazes, consisting of several non-linear screens. So when you move out to one level, you can get into the same level as you can get if you enter to the right. So it's really you've got to learn your way by this turn, that turn, and not by just thinking as just as a plain area. There are several connecting rooms, like forks, so where you can get either to the maze or to the castle. There are some dead ends. Some of them might contain objects that you need to solve your quest. So let's take a look at these objects. All objects interact by overlapping, so touching. This was something very new back then. We've got 3 dragons who chase you. This one is the real enemy. Because it moves your object away, you can carry only one. And so if you put it somewhere, it steals it from you. So maybe the sword is gone when you want to fight a dragon. You've got, for each of the 3 castles, you've got a key. A very nice drawn sword to kill the dragons. This is something really cool. This is a wall where you can cross through, a bridge where you can cross through horizontal walls. The magnet to attract objects. This is also something very nice. This is a workaround for a problem you've got. You can drop some of your objects inside a wall so that you can't get them anymore, or the bat can do this. So you gotta get it out there somehow, and this is why Warren has implemented this magnet to attract the objects. And of course, you've got the enchanted challenge. So, but the coolest thing about adventure is there's one more object. It is 1 pixel in size and has the color of the background. So if you drop it, it's really hard to find. It's hidden in a room that's only accessible using the bridge. So in normal gameplay, you even wouldn't come to this room. When you take this dot to a certain room and add another object to this room, the wall is gone. Maybe not on the first time, maybe you've got to leave the room and enter it again, but then the wall is definitely gone. And if you go to this wall that is now gone, you can witness the first Easter egg of video gaming. The revenge of a disgruntled video game programmer. When Atari released their games, the programmer of video games got a salary of about 20 to 25K a year. And they didn't get their name. Not in the manual, not in the game, not anywhere. It was an Atari game, it was not a game of a programmer. So Warren chose to hide this one very deep in there. And after that, quit. So let's take a look on how you're going to program it. Back in '77, you've got code assembled on a computer running a proprietary OS. My guess was that it was CP/M, but it wasn't back then. It's connected to a special cartridge which simulates the ROM inside the Atari. And when the software crashed, you would just see stripes top down. Why? We're going to learn later on. For debugging, a logic analyzer was used. So something leading to a special condition could be displayed. It does not need the crash, but something else could also be done. Nowadays, it's much more simple. You've got your code assembled on almost any operating system you're going to choose like. You can run your code inside a very in Stella with an emulator with very sophisticated debugging options. And once it works like expected, you can transfer it on a special cartridge, which simulates the ROM for you. Supercharger was the first who was able to do this, and Harmony Card is the current one that you can buy. In between, there have been about 4 other cartridges, but they are not available anymore. So this is what the supercharger looks like. The data is transferred very much like it was done on the home computer back in the 80s, so with an audio-coded signal. The game developers mostly use this to plug in the audio signal into the sound card so that could create the data direct from there. This is what the debugger looks like. So you got your source, your object code, you've got all the RAM in one view. And you've got the display of the game. It turns black and white once the new screen will be drawn, so that you can see where you are going to draw your data right now. Piracy. It was even back then an issue. In the design phase, nobody thought about it because they thought this hardware is so sophisticated, no one ever will be able to hack it. But suddenly there was competition in the name of Activision. Activision was founded by 4 Atari programmers who decided that they wanted to have their name on the cartridge, so they had to go independent. And there was a nice talk before they did that, and this sentence was the one that really got them going. Well, Atari and otherwise. They filed a lawsuit to prohibit third-party game development, and they lost that suit. And other companies, know that the jurisdictional stuff was clear, jumped into that and really lead to a flood of game cartridges by other programmers. Some of them were really nice, but most of them were not really worth mentioning today anymore. So, but when you have the option to program for it, you have also the option just to modify the game. So this is the cause of all the bootlegs. You just pick out the original game, maybe change some sprites or some colors, and then you have a new game that you really want to sell as new. But you could also copy your games at home. There was some kind called the duplicator. You have got cartridges, they are fit with an EEPROM, and this is just an EEPROMer with very special connectors. Atari filed a lawsuit, and this time they won. It was a pretty bit too obvious that this is not really good. So, homebrewing. The Atari has been out of production for 20 years now, even more. And there's a big homebrewing community that still develops new titles. This year, Boulder Dash has been ported as a licensed game from First Star Software. Atari Age and others sell real cartridges that you can buy and plug in an original Atari. More than 100 titles. Compare that to the 500 titles that were available when the Atari was taken from the market. And most of the homebrew games are even better programmed. So if you want to do it yourself, I can recommend 2 different assemblers. There's the DESM assembler, and this is the de facto standard of the homebrew community. And there is the CC65, which comes from another aspect, more for programming for Atari, the Commodore computers, the 8-bitters, all what runs on a 6502 processor. And if you just want to give it a hack, there even is Batari Basic. This is a basic-like language which compiles your code to an assembler source code that you can put on through DESM. You don't want to write a new game from scratch. you can go hack and modify other games. You can just change the graphics as the bootleggers did. There are even a few games with editors, so adventure can be modified to your own adventure. And you can disassemble a game and modify it. And therefore, I've got a fine example, Pac-Man. This is what Pac-Man looks like in the arcade, and this is what Pac-Man looked like at home. So the homebrewing community thought, we're going to do this better. Let's put it in this way, so even that the colors match, the sprites look a bit nicer. But they even took another step. This is the ROM image of Miss Pac-Man, the successor, and they put back in the original image and even put in intermediate movies and stuff like that. It's really close to the original arcade version. So let's take a look at the hardware. This is the block diagram. So we've got the Atari, we've got the ROM module that contains all the code. There's no firmware or something like that in the Atari. The Atari in itself is dumb. You've got your input devices like joysticks and pedals. And you've got your output device, the television. Inside the Atari, we have got the 6507, the CPU. We've got a chip that contains RAM, I/O ports, and a timer. And you've got the television interface adapter. These are all connected through a CPU bus. And the input devices are connected to the Riot, and some also to the TIA for analog inputs, something like that. And the TIA outputs what you've got to the television. So let's take a look at the CPU. The CPU is a stripped-down version of the 6502. This has been described in depth by Michael Steil last year. And I really, if you want to go into that, I really recommend that you're going to see that talk. So here's just a brief overview, first of the 6502. It was designed by Chuck Peddle, who also did some work on the Motorola 6800. So that was one of the causes for the lawsuit I mentioned earlier. It is an 8-bit architecture, a little endian. Your instructions take up 1 up to 3 bytes and take 2 up to 7 clock cycles to execute. In this case, it is clocked at about 1.2 megahertz. And it's cheap in production, even the 6502, and it was competitive in speed. So you've got in the CPU 6 registers, the multi-purpose accumulator, 2 index registers, the program counter, so where the next instruction will be fetched from, the stack pointer, and there are some discussions if it's a 16-bit register or not. It is a 16-bit address register where the next address for stack will be used, and it is an offset from 1/800. But if you transfer the stack register to, you can transfer it to the X register, and then you have got 8 bits, so I chose to say it's an 8-bit register. And you have also the processor status for the 0 flag, negative flag, stuff like that. So what's different about the 6502? It has a smaller chip package. What's missing? 3 address lines. So instead of the 64K, you've got only 8K where you can put, that you can address. All the others are mirrors. The both interrupt lines have been completely disabled. There are 4 other pins missing. They are not essential, and 3 non-connected pins have been missing. And this one is even, because of the smaller chip design or chip package, this was one of the main cost factors you've got back then. So it was even cheaper to produce than the 6502, and it was very popular for embedded applications like washing machines, something like that. So we've got the Riot. It was a very, very, very common companion chip to the 6502 family. It features the whole 128 bytes of RAM. That's all you ever get there. You've got 2 I/O ports. One port is used for the 5 console switches, the one you saw on the first minus the power switch. You've got 1 I/O port for both joystick ports. There are only the directions. The fire buttons are routed to through the TIA, and a timer that is capable of sending interrupts. But as we have learned, the 6507 is not capable of receiving. So the external address space is 8K. This means we've got 8 mirrors. The remaining address space is split in half. The lower half is used for I/O, like the TIA, the Riot, timer, RAM, and the other half is used for the ROM module. They are typically used in two ways. Either you put them all in one, but the most common one was to use the lower bank with the address of 0 and the upper and the ROM with the address of F. So this is what the mapping of the chip looks like. It's a bit weird, so it's usually addressed at the first part of the 0 page. There are different shadows available. It's got space for 64 registers. There are 14 read-only registers. They are mirrored 4 times inside that 64-byte address space. So, we've got 45 write-only registers, and they're really write-only because if you read from the same address, you get the read-only registers. So I use address for both of them. So this is what the exact mapping of the Riot looks like. The real interesting part is that the mode of is either RAM or I/O. So it means it's mapped to 2 different addresses. The RAM is usually addressed at the second half of the 0 page, and the I/O is at 280. So this is the mapping, which looks a bit weird, but they're alternating like this, that you get the first 2 mirrors for the RAM, the second 2 for the I/O, and then switch back and something like that. This was necessary to get this mirror here. We'll learn short why. So this is the I/O ports and the timer addresses. This is the RAM, 128 bytes, as I mentioned. It's needed at 2 locations. For your game status, the variables, and for the stack, which is at 180. So what you've got there is pretty less time. In the manual, it is stated that the stack will be used from top FF down. So keep in mind that you're using mirrors, so that you don't have that 128 bytes twice, but only once. So, and my favorite quote from the developer's manual is this one. So, what's still missing is the ROM. The ROM resembles, with its 24 pins that are on the connector, resembles an EEPROM or a ROM of 32 kilobit, so 4 kilobyte. It has three power lines, two ground and 1 voltage, 8 data lines, and 13 address lines. So it just resembles. What's the difference? What's missing? What's missing is the chip select signal. So what Atari did, they just defined that the chip select is not low active but high active, and it's used at the highest address line for this use. So they needed no logic inside the Atari to generate a chip select. And what's also missing is a read-write line, which is, in my opinion, is a bit of a design fail because they have 2 grounds. One would have been enough, and they could have used the read-write so that you could put RAM on a cartridge. But this was, when they designed it, they just thought of it, 4K of RAM would be enough for everyone. So we're going to need now learn about how to work around these barriers. At the start, there were only 2 or 4K ROM modules. At 81, the first 8K ROM modules were available. How are we going to fit it in there? Bank switching. Let's assume you've got your ROM, which is an addressable space of 4 kilobyte. You put in 2 banks, and by reading just from a special address, you switch from one bank to another. And by reading from another address, you switch back. This is called the F8 type of cartridge because of the low byte value that's been used for switching. So, if you need more ROM than 8K, you can simply add more banks. You use 4 banks and again 4 hotspots for accessing. This is called F6 because the first one was F6 to use. Now we have enough ROM, but what about RAM? We have no read-write line on the module. But we can use or misuse the address lines for the read-write configuration. So we have a write port and a read port. The write port starts from 1000 and the read port starts from 1080. So what we're going to write to 1000 can be written from 1080. And these are variations of the cartridges that I just introduced, and they have added SC for, as far as I know, super cartridge. So, but you can put, you can push the bank switching a lot more further. You can first try split up your address space so that you don't need to bank all of it at once, but just one half. For this, you can address up to 256 banks, and these are not addressed by accessing hotspots because a whole page would be just lost for hotspots. You write the ROM bank number to 3F. This is I/O space. But since you've got the whole CPU bus, you can use it. You can also add 32 banks of RAM. Change it to a different I/O address you're going to use, and then you've got a really super cartridge which is capable of addressing 512K of ROM and 32K of RAM. They are the different ports. And this is called type 3E because of the RAM address, and it was used by a company called Tiger Vision. Though they didn't push it this far, as I could research, they only used up to 4 ROM banks. But one of the homebrew cartridges was capable, or they have extended this logic to use it up really to this maximum. So, short conclusion. There are many ways you can get more ROM or RAM into the cartridge. There also include some kind of bank switching scheme. And you've learned about 5 real-life configurations. The emulator Stella allows about 25. So it's even fun just to poke through the source code and see how they implemented the bank switching. There are some really weird things there. So, and nowadays you can use it using microcontrollers in cartridges, which also include the ROM data then as well, which is used in the Harmony cartridge, for example. So, part 3, how to write programs. Now you're going to learn how to write on the registers. But first of all, we need to look at what a television frame looks like. The ray crosses the beam crosses the frame from left to right, and while it's crossing, it is selected which color should be displayed. And this is done line by line, every frame. For these scan lines, as they are called, you've got on NTSC 262 and on PAL 312. Across as the beam travels, you've got 228 color clock cycles. The Atari has no frame buffer, as most of the other consoles. This is one of the main differences. So you cannot call them pixels or something like that. So you've got your vertical sync from the television, which is not displayed on the screen, as well as the overscan area, where the beam already has gone out of the picture. And you've got your horizontal blank, which you can use to prepare something for display. So this leaves you with a drawable area of 160 color clock cycles. So this is what you, well, the closest one you can get to a pixel, so this is the resolution you've got there. Your game's logic will always happen in the vertical sync, vertical blank, and in the overscan area. During this phase, you have to draw the display yourself. And the CPU clock, when you program the TIA, you have only 76 color clock cycles, exactly a third, because the color clock, the TIA generates the CPU clock as 1/3. So, since we've got no frame buffer, well, why we have no frame buffer? RAM was in 75 very expensive. My rough guess is that a kilobyte of RAM back then costed more than it would cost a gigabyte today. To convert, if you think of it as a frame buffer, the 160 times 192, you will need 30K of 7-bit words. This would be a huge amount of RAM, this would be very expensive, and it wouldn't even be addressable by the CPU. So, a completely different approach has been taken. You program the chip while it is traveling the beam. The advantage is, it is very cheap, was very cheap to produce, and it is very flexible. So, over the years, the programmers really learned to master this technique. And the disadvantage is, as I stated, the CPU is occupied during display, so you can't do any game logic in there, except you put in a blank or something like that. So instead of running the graphics frame by frame, the image is drawn really line by line, and you draw it line by line. When nothing changed, the next line is drawn as the one before. So if it crashes, you have just one set of lines going from top to down. There are no registers for Y components. That was something that was really odd to me when I started reading the manual. I thought, yeah, the sprite position X and where's X and where's Y? Y as you draw. So when you draw a sprite, it is 8-bit wide, and you can put it as high as the screen. So what you do is you tell the TIA to paint while it is painting. And this really needs some exact timing, and this is officially called racing the beam. So let's take a look at the white registers. There are 4 for syncing, so you even do your own syncing on hardware. A lot of graphics registers, a bit audio, and this is to reset collision. So let's take a look at the graphic capabilities. You've got a background color, you've got 2 different colors for the sprites, you've got playfield with its own color, you've got 2 missile sprites that are reusing the player colors, you've got 1 ball sprite. So if you take a look at this, a ball, 2 missiles, it really comes from the requirement that you needed to run Combat and Pong as games. So let's take a look at the colors. We have got 4 color registers, background, the playfield, and the 2 players. All other colors are taken from these, for missiles, and the ball are taken from these registers as well. And the color can be picked off a palette of 128. As a C64 programmer, I was really envious of this. This is what the palette looks like on NTSC. This is what it looks like on PAL. Because PAL color generation is more complicated, some of the space needed to be used for this logic, and so it was completely rewritten at this point. When you port a game between NTSC and PAL, this is one of the 2 things that you've got to take care of, so that you use another color palette. The other is the 60 Hz versus 50 Hz timing problem, but this really isn't a problem. As you have seen, you do the timing all in software. You really program the video blank yourself, so you've got no problem in running an NTSC game in a PAL console. You just get a 60 Hz version of the game, and you get some really strange colors. But really screwed were the one who got a CCAM system. What has happened there? Well, the Atari has a switch in which you can put each game into a black and white mode. So on the CCAM system, this switch is always set to black and white, and instead of displaying different gray colors, it's just really a different color that's been used. So let's take a look at the playfield graphics. The resolution is 40 bits, so we've got 4 color clock cycles per bit that's been displayed. The register responsible is the playfield color, 3 data registers, but how are we going to squeeze 40 bit into 3 bytes? There's one more register that is involved, it's a control playfield register. And there you've got the option to reflect the playfield or repeat the playfield. This we're going to get in depth on the next one. You also can choose that you can use the player colors for instead of the playfield color, which has been often used to display the score of a game. So the left half uses the number displayed on the left gets the color of the left player, and on the right gets the color of the right player. And can also choose the priority if the playfield should overlap sprites or if the sprites should overlap the playfield. So this is the data register in depth. We've got our 20 bits there, this ordered in this way. So these 20 bits can be either mirrored, so that you can, and yes, this is not a mistake, the bit you specify there is really displayed somewhere in the middle. And this is one thing that's also it's the cause for a lot of bugs if you're going to try coding. At least that's been for me. What you can also do is repeat the same color, still unordered, or sometimes reverse, sometimes normal, and back to reverse. But what you can also do is you can change it during display. So while the beam travels over has displayed the first data, you can change that data to something completely different, and then use this data again on the right half. Well, and this ordering really isn't anything but straightforward. So let's take a look at some examples for our playfields. This is a classic combat, which has been one of the launch titles. You've got the playfield slightly mirrored. You've got your different colors for the players and the player sprites. Defender is a nice example on how the repeat has been used to draw the screen. And one of the nicest examples that I could use for playfield was a game called Tutankhamun. There they're going to use the alternating between mirrored and repeating to really design the game levels. So you come back from up there. You've got here a place where it is switched. This is a tunnel. So you can't go back down there. You go through the tunnel, go down there, and yes, here it is mirrored, here it is repeated. And this is something which I think is very clever design back then. We've got the playfield, now the other big graphic elements, the sprites. The tier has 5 sprites, 2 player sprites, 8-bit, 2 missile sprites, they are on or off, and 1 ball sprite, also just on or off. So the missile sprite positions can be locked to the player position by register, so that you don't have to use the registers as for the missile sprites, but can position them on the same position as the player. And keep in mind that this was that the hardware was constructed for using combat and Pong. So here we're going to see the player, the missile sprite, the player, and the ball sprite, and these are also player sprites. Sprite placement. This is a real interesting topic. The Y is how it reaches when it's enabled before it reaches the beam position. And X is really a bit more complicated. You have registers that are called reset player 0, reset player 1, reset missile 0, reset missile 1. But these are just registers you trigger. They don't take any value. They just reset the sprite position. And reset has also a different interpretation in here. You do not reset it to position 0, to the left, but to the current X position of the beam. So what you're going to do is you wait till it reaches a special position, then trigger the reset register, and in the next line you enable so that it is displayed. But we have learned that the tier is 3 times as fast as the CPU, so you cannot do it pixel or color clock cycle exact. For this, you've got fine-tuning. We've got fine-tuning registers. These are motion registers that can be used to move the sprite -8 to +7. Very intuitive. Negative moves to the right, positive to the left. And you just store a value in there. It is not triggered while storing. It is triggered by storing the move register. And you can clear all these values at once. So how are you going to keep your code in sync? This is something that is really essential, as we've learned on the previous slides. To accomplish it, there are these 3 rules you're going to use. First of all, you count the cycles. You know of every instruction what it takes to execute. The second one, this is the core. This is really the core of Atari programming. You've got the W-sync register to stop the CPU until the start of the next scan line is reached. So you can always delay your code to the next line about to display. And this is something, this is the key that obsoletes, or not obsoletes, but makes it possible to work without interrupts. And if you cannot predict, well, don't want to predict because it is some more complicated game logic, you start up a timer, run through your code, and wait for it to time out afterwards. So let's take a look at some real-life sprite examples. So the question is, 2 player sprites is really a bit, not much. So we can get more sprites. This can be done in software, just by changing the sprite registers once a sprite has been displayed. But you can also get a bit of help from the hardware. This is another game variation of combat. And once you've got 3 planes there, again, 1 large one. And this is done by hardware registers. The player sprites, well, for the player sprites, we've got these 7 options. The normal sprites is mostly used. You can then position them or enlarge them. So mirroring is also possible, that you don't waste your ROM on mirrored data. And the ball and missile sprites can be enlarged. So let's take a look at some game examples. Outlaw is one of the, not a launch title, but came really short afterwards. 2 player sprites and missile sprite has been used. Circus Atari is quite nice. The player sprites are used for the 2 clowns, and the seesaw you can see there is a missile sprite that's been moved 4 pixels, or 2 color clock cycles, sorry, every line. So you've got Berserk and Vanguard. They use the same technique. They make sure in gameplay that no 2 enemies are on the same scan line. If this robot moves up, you're going to get there, it will stop about here because it would then reach the area of the next enemy. Pac-Man uses another different technique. This is a bit bad to see here. Pac-Man is always drawn every frame, but the ghost, 1 there, 1 there, 1 there, and 1 there, are also drawn, they take turns in being drawn. So they are interlaced. Space Invaders uses another neat trick. It uses triplication. So this, and this is the same sprite, and this, and this is the same sprite. And what you're going to do is, when someone gets shot, you don't turn it off, but you set the data to 0. DigDug is a really fine-coded game. It just uses interlates when two sprites are on the same scan lines. Video chess uses another trick. It displays only every other line. So, and this is really still the best technique to use if you want to generate some kind of menu or something like that to display your data. So let's go to detecting collisions. This is essential, and the hardware is full-featured here. We've got all combinations that are possible for collision. They are registered in there. They will keep their data until it is triggered. What is a collision? If you code it in software, you would do it would not if the pixels touch, but you would take the drawing area and just see if something matches there. But the Atari is really good there, so this is not a collision. We've got two voices. A little bit of a rush because time is running out. The audio, we've got two voices, each having 3 registers. Volume, the frequency, this is a divider for the base frequency, and the control. The control has 11 unique settings and is a basic, or controls the basic pattern you're going to get there. You're going to see it a bit later afterwards. Most of the settings are not used for music, but just for motor noise, shots, and something like that. So the sound generation can be looked in at 2 steps. The basic signal is generating by setting the audio high or low. So what the output got in there is just a rectangle. These are the base frequencies that are used. The control registers define the pattern. And the sound is generated by shifting these patterns out one by one. So let's take a look on a piano keyboard on what tones you've got if you're going to use the settings that are used for generating just a pure rectangle, and they are used for generating a melody. So what you've got there is a bit more than 3 or 4 octaves, something like that. And some game developers really took some guys, say, write me some simple music, and instead of taking something that has been already known, because there are some keys sometimes missing. So let's take a look at the waveform that can be generated. So this is the pure rectangle you get for the high notes, and this is the one that you get for the low notes. And some others are really weird looking, so they get some kind of distortion that can be used for motor noise and something like that. So, and the step 2 is that this signal is multiplied with the corresponding volume register. And this can be used also to play 4-bit digital data. This is quite impressive. There is one game which is really worth looking at. It's called the Berserk Voice Enhanced Edition. This is a hack of the game I introduced during the sprites part. And this features the voice of the arcade version. And if you compare it, it's really impressive because of the really different hardware and the capabilities. The hardware is way more, of the arcade version is way more sophisticated. So, going from here, what you're going to do next? I invite you, play a game. Back then, you couldn't hide a shitty game behind beautiful graphics and a beautiful soundtrack. When a game sucks, you see it, and if it doesn't suck, if it really gets you playing, then it gets it for a good cause, because the game is good. I've not covered the homebrew games because I'm already out of time. And take a look there. It really is impressive of what the homebrew community has squeezed out of the hardware. And what's also nice, what you've learned here, try to figure out how they do it. I still have seen some games, I don't know how they did it. So, if you're not into playing games, play with the system, code something for free. All tools are available. The emulator is available with very nice debugging support. You've got 2 assemblers you can use. And From the intro, I've displayed the scroll routine without the coloring. Just drawing some text has taken me an afternoon to code. So it's some time you can spend. If you think the Atari is shit, do a talk about another console. I would like to learn. Show me something. So, have you taken time for questions? No time for questions. So I'm sorry, but I wanted to squeeze as much information as in the talk. I'll be here around. I'll wait outside the room. If you have questions to me, address them. I'll be waiting there for you for about the next half an hour. Thank you.